Hi, so here's the video about basic sine cosine graphs quickly and essentially about their transformations. Let's review the basic sine and cosine graphs, and also if you forget, if you mix them up, if you don't have a calculator in front of you, how to quickly figure out which is which. So on the unit circle, and also reviewing how to label the x-axis. So the initial rotation position is here, 0 radians, and then we go counterclockwise, and the entire circle is 2 pi. So this is pi over 2, and this is 3 pi over 2. So that's how we are labeling our x-axis. We really need 4 sections, 4 equal parts: 2 pi, the entire cycle, half of the cycle, quarter of the cycle, pi over 2, pi, 3 pi over 2. Okay, so when we graph our function, starting here, this is our sine graph. So sine is the vertical coordinate, the height of this. We start at 0. As our point rotates around the circle, the sine, the y-coordinate, is increasing and reaches the maximum 1 at pi over 2. So let's label this 1. This is negative 1. Then our sine value becomes lower. It decreases to 0, and it becomes 0 at pi. And then it goes down and turns negative and reaches the lowest, which is negative 1, at 3 pi over 2. And then it's still negative, but it's getting closer to 0 and reaches 0 at the end of the cycle. And then we connect it with a nice and smooth curve. And if we need, we can extend it either way. Okay, same thing with the cosine graph. So 0, pi over 2, 2 pi over 2, which is pi, 3 pi over 2, 4 pi over 2, which is 2 pi, and the same here. 2 pi, pi, pi over 2, 3 halves. Okay, and again we will need 1 and negative 1. Okay, this time cosine is the x-coordinate of the point. So as we start at the initial position, this is our cosine, which is already at its maximum at 1. Now, as we rotate around the circle, cosine value is getting lower. It's getting closer to 0, and it reaches 0. This is the x-coordinate here, at pi over 2. And then it goes to the negative side. The cosine value is getting, by absolute value, bigger and bigger, and reaches the lowest, negative 1, at pi. And then it comes back to 0, and then it becomes positive again and increases to 1. So connect it nice and smoothly, and we have this specific tulip shape. And of course we can extend it if you need to come back. Oh no, wrong way, this way. Okay, so let's look at these two graphs. A key part: each cycle, which is 2 pi for basic graph, is divided into 4 sections. For sine, we go up, down, down, up. For cosine, we go down, down, up, up, tulip shape. The y-intercept for sine is 0. The y-intercept for cosine is 1. So that's what you need to remember, because these are the graphs you're going to transform. Now, when you talk about transformations, it's different than for other functions. Imagine taking a complicated curve, as it is already, and now translating it up or down or left or right, or shrinking or stretching. Either way, it's not easy. This is why we are doing these transformations by manipulating the control numbers of sine and cosine functions. So these are our control numbers. The equation of either sine or cosine, I'll just use sine, but essentially it will be the same. In most general form, where everything can be changed. All control numbers can be changed. Looks like this. I stretched it because I'm going to annotate all these letters. 4 control letters. Now, this one, C, you are not responsible for graphing it, but you need to still understand what it is. Okay, so let's label what each of them is. When you multiply a function by a number, it's a vertical stretch. Stretching or shrinking? Stretching or shrinking. Okay, now, but we physically do not take a graph and shrink or stretch. This is hard. So what we know is that A is an amplitude. Not really the A, but absolute value of A, because A itself could be negative. So this is amplitude. And the amplitude is 1/2 of the height. This is what we need to know for graphing. Let's take care of D first, and then we will talk about the harder stuff in the middle. When we add a number to a function, this is the vertical shift. If it's positive, then up. If it's negative, then down. Okay? But we're not physically shifting a graph. We just know that D, or rather y equals D, is the equation of the midline, or it's also called the axis of oscillation. And that's what helps us graphing. So let's take an example with just these 2 control numbers, just these 2 transformations. So let's take y equals 3 sine x plus 2. Okay, so the amplitude is 3, and the midline is not a 2, it's a y minus equals 2. This is the line. So this is your midline. So that's what we're going to use to graph it. Okay, first we need to scale the axis. Because my frequency, there's nothing here, it's a 1, so there are no horizontal transformations. It's a basic horizontal scale, so we need to label it 0 to pi, that would be my cycle. Again, pi over 2, 3 pi over 2. Sometimes we need to go more to the right, to the left, but let's not do this now. And the vertical scale should be labeled scale, but I'm not sure yet how. Let's look. So I'm going to draw the axis of oscillation, or the midline. Y equals 2. So, okay, this is 2 then. This is 1, 2, 3. Okay, so we're going to draw the axis of oscillation. And I will label it so I remember what it is. Y equals 2. Now, we're looking at the amplitude, and we are saying, all right, so my amplitude is 3. That means that half of the height of the graph is 3. In other words, my graph will go from the axis of oscillation, 3 up, 3 down, 3 up, 3 down. So it may be a good idea to draw a boundary, so 3 units higher from the axis of oscillation and 3 units lower. You may not want to draw it, but just take a note of it. So I need to keep labeling my x's though. 3, 4, oops, I don't have enough room. Okay, 5, -1. And now the next important step. Normally my graph starts, sine graph starts at the origin, goes up, down, down, up, and comes back to 2 pi. But now it will not oscillate about the x-axis. It will oscillate about the new axis of oscillation. So it will start where it would start originally, but 2 units higher, which is on the axis of oscillation. And then it will be ended, it will complete the cycle at the same position. And the middle position, as you know, will be halfway. So again, instead of crossing the x-axis at 0, pi, 2 pi, it will cross the midline at these points. And from the initial point, it will go up, but it's stretched 3 times. So it will reach my yellow line, which is my boundary, halfway between 0 and pi. So at pi over 2, it will reach the highest, and at 3 pi over 2, it will reach the lowest. And then I'm going to connect my 5 points. Okay, so up, down, down, up. If I need, I may need to repeat this cycle, either the right or on the left. So we, as you see, did not really use transformations. Transformations are used kind of implicitly. Our amplitude tells us that instead of going up and down by 1, it goes up and down by 3. And the midline tells us that the entire graph with its axis of oscillation shifted 2 units up. But if you understand how these control numbers work, we don't really need to think about transformations anymore. We just fit our basic sine curve or cosine, same way, into these horizontal and vertical boundaries. One full cycle and maximum and minimum. Now, what if my original equation had a minus here in the front? So the amplitude is still 3, but the minus is responsible for reflection over the x-axis. So whatever was positive will now become negative and vice versa. So all I do, I just flip my graph over, but I'm not just drawing it by hand. I'm reflecting those important 5 points. So these points, they don't need to be reflected because they are on the axis of oscillation. The maximum becomes the minimum, and minimum becomes the maximum. And now I draw it neatly. So this is my negative 3 sine x plus 2 graph. And the original was positive. Where's my minus? Over here. Okay, let's look at the harder transformations now. Okay, focusing on B. So you know that when the number multiply in general, let's say if you have y equals function of, let's use the same letter, bx. Because it's multiplication, it's like stretching or shrinking, and because we multiply x, it must be horizontal stretching or shrinking. So in terms of transformation, it's easy to say. So B is responsible for horizontal stretching or shrinking. But this is probably the hardest or one of the hardest transformations to do physically. How do you shrink or stretch the graph? This is why we are using a specific language for sine cosine graphs. B is called frequency, and what this frequency is, it's a number of cycles that fit in one 2 pi period, or 2 pi interval, 2 pi interval. So frequency of this graph is 1, not only because the number 1 is here invisible, but only because we have one full cycle that fits into 2 pi interval. If there is more, then the graph will be oscillating faster. How much faster? B times as fast. In other words, if you want to find the period of your new graph, we start with the 2 pi, and then we divide it by the number of cycles, by B. This is a very important relationship. So let's say I want to change the frequency of my graph. I'll make it 2. Okay? So think about all aspects of this concept. Look at the definition first. Frequency. Number of cycles that fit in one 2 pi interval. So there should be 2 cycles that fit into a single 2 pi interval. So my function now will be twice as fast. It will oscillate twice as quickly as this one. this itself can help you graph, but it's much easier if you actually calculate the new period. So period of my new function will be 2 pi divided by frequency, which is 2. And it's 2. You could figure it out without really dividing, because if the original is 2 pi and it fits twice, then each period should be pi. So now this pi is my full cycle. So what I do the same as I did with my original period. I divide it into 4 equal parts. I don't have enough room to label all of this, but I know that each of this will be corresponding to a quarter of a circle. But my circle will oscillate faster now. So instead of reaching the highest at pi over 2, it will reach the highest twice sooner. And then it come back twice sooner, not at pi, but at pi over 2. So this is my first loop. And then it needs to finish the entire cycle by the time it comes back to pi. We can think about shrinking here. Instead of this far, it goes like twice closer to the x-axis. But this is not an easy technique. It's easier to say, all right, so my cycle, let me make it more visible, is 4 sections now. So my 5 points, beginning of the cycle, quarter of the cycle, middle of the cycle, next quarter of the cycle, and end of the cycle. Maybe I should make my graph black now. Let's do it again for the next cycle. So I divide it into 4 sections. Beginning of the cycle, quarter of the cycle, the highest point, back to the middle, the lowest point, back to the middle, connecting them. So you can see now that there are 2 cycles, 1 and 2, that fit into 1 2 pi interval. That's what frequency means. Let's look at a couple more examples. So here in the first example, the first step to write all control numbers, amplitude 1/3, axis of oscillation, y equals -1/3. Now B frequency is 1/2. We cannot, we can, but not directly graph just looking at the frequency. We want to calculate the period. And period, as you know, is 2 pi divided by frequency, so divide by 1/2. In other words, 2 pi multiplying by 2, which is 4 pi. You don't need these formal computations if you understand that frequency says it goes half as fast, in other words, twice slower. So it will be only one half of the cycle instead of the entire cycle within 2 pi. But computations definitely helps to confirm and visualize this. So we need to graph one cycle. So technically I could just start plotting 4 pi anywhere. This is my period, and then divide into 4 equal parts. But because I have graph paper here, I can be nice and just make it more or less. I have space, and I want to show that the graph stretches, so it's this will be my 4 pi. So half of it is 2 pi, quarter of it is pi, and 3/4 3 pi. I don't need to label more. This is what's important. Now, let's take care of the vertical of the shifts. So I'm graphing my -1/3, the axis of oscillation. I don't need to find 1/3 of a box. I can just say that this is my 1/3. Okay, and this is positive 1/3. And then, I cannot, because then I need to go from -1/3 up and down, and I don't have room down, so I'm going to change it. So this will be my -1/3. And this is positive 1/3. And once again, so I'm drawing this level. This is my axis of oscillation, y equals -1/3. From here, I'm going 1/3 up and 1/3 down. So that corridor, which I don't really need to draw, but it might be useful, that shows my oscillation 1/3 up, 1/3 down from the midline. That tells me where the oscillation will be contained. Okay, now this is cosine graph, so this is my tulip shape. But I'm not just drawing it by hand. I'm marking my 5 important points. But for cosine, it's not the same as for sine. So the highest point, the lowest, the highest again, and halfway at the quarters. So I start at the highest point here and end at the highest point. So the lowest point halfway and quarter way is my middle points. Okay, and now I'm drawing it as a tulip, nice and smooth, so I could extend it if I need to. Okay, so this is my graph. Before I continue with one more example, I just need to say, yes, you can graph all of this with a calculator, but on a calculator screen, you just see a curve, and you cannot just on your test just draw something like this. Ooh, copy in my curve, something like this. No, you cannot do this. You really need to start with the scaling. You need to mark important points. This is why, yes, you can check yourself with a calculator, but you still need to understand these techniques. Finally, one more example. I left everything unchanged, so the amplitude 1, nothing to add, but I made this B kind of hard, or at least it looks hard. So frequency here is pi over 2. So what does it mean? We don't need to think much. We can just calculate the period, and then it will be clear. Period is 2 pi divided by frequency. So I can dividing is multiplying by the reciprocal, so I multiply by pi, 2 over pi. Oh, there was 2 pi. I can put it over 2 to see better what's happening. Pi cancels, and I just have a 2. So what it tells me is that my period is 4. When you draw it, you will see, you will better understand what's going on. So I prepare the coordinate system. 4 is the period, so it's a full cycle. I, as always, divide it into 4 parts equally, and it's easy to see. It will be just 1, 2, 3, 4. And I'm just fitting my cosine curve. The amplitude is 1, so this is my highest, this is my highest, this is my lowest, and halfway. So this is my curve. That's it. So you don't need to worry about anything really, just if you follow this procedure. But I want you to just make one more note. Frequency, we said, is how many times the number, how many cycles fit into 2 pi interval. Let's see. Pi over 2 is 314 divided by 2, which is 1.57, approximately 1.5. And where's my 2 pi interval? 2 pi is 6.28. So if this is 6, then 2 pi is somewhere around here. If you extend your curve, you're going to see that from here to here, you will have approximately 1.5 of the cycle. So pi over 2 is more than 1, but less than 2. So it's more than 1 cycle, but not 2 cycles yet. So everything makes sense if you just understand the fundamental ideas. Good luck with graphing.